Hi physical science students, this is my podcast about Newton's third law. We learned that Newton's first law states that an object will maintain its state of motion unless acted on by an outside force. Newton's second law told us that bigger objects need more force to accelerate in the same way as smaller objects do. And Newton's third law states that for every action force there is an equal and opposite reaction force. So examples of these action and reaction force pairs are all around us. They're around us when a balloon travels from one area to another. I'm not going to talk too much more about the balloon because you're going to be doing a lab that requires you to think about that action and reaction force. So let's think about it in terms of a trampoline. When you jump on a trampoline, you exert a force down on the trampoline. It is exerting an equal and upward force on you. If you use your finger to push on a wall, you are pushing on the wall with, let's say, 10 newtons of force, and the wall is pushing back on your finger with 10 newtons of force. So in other words, we need to think of forces, when we're talking about Newton's third law, we need to think about forces happening in pairs, and we're not talking about forces that are occurring on the same object. And we'll get more into what that means in a little bit. But let's look at some more real-world examples of forces happening in pairs. Here's a nerdy scientist, and he's being pulled downward by Earth. No surprise in that. That's what gravity is all about. So that's an action force. But the reaction force is that the Earth is also being pulled upward by the scientist. The scientist also exerts a gravitational force on the Earth. Gravity is just a force of attraction between any two objects. The more massive something is, the stronger its gravitational force is. So the scientist is the Earth is exerting a force on the scientist, and at the same time the scientist is exerting a force on the Earth. So you might ask, well, why doesn't the Earth get pulled upwards then? Well, it does slightly, but the Earth is so much more massive you don't even notice it. But you definitely notice the force pulling you down. That's what gravity is all about. So gravity is a great example of an action-reaction force pair that we can talk about. So that can get a little bit confusing because if I'm exerting a force on something and it's exerting that exact same force back on me, if I'm pushing on a wall with 10 newtons of force and it pushes back on me with 10 newtons of force, if all the forces are balanced, let's say, how can anything move? Well, we know that equal forces don't always have equal effects. So when you watch the video about the science of golf, it'll give you a great example of how when you hit a golf ball, you're exerting, let's say, 500 newtons of force. I just made that up. For a split second, that golf ball is exerting the exact same amount of force back on that golf club, but the golf club's way more massive than that golf ball is, and so it is able to deliver that force in a very short amount of time. And so you don't notice the ball pushing back on you so much. You'd notice if you swung at a golf ball and you missed, like what I do. You notice when you swing at a golf ball and you hit it, you can feel that force come back at you. So there is another example of an action-reaction force here. Which brings us to this term momentum. We talk about momentum and we use it in everyday life, but sometimes we don't know exactly what it means. Let's get this clear. It's not the same thing as inertia. Momentum is a property of all objects, and inertia is a property of all objects. Remember what inertia is. It's the tendency of something to keep on doing what it's doing. Either sit still or move with a constant velocity. Momentum, though, we can define it as mass in motion. And a great example is if you were to play pool. A pool ball has momentum as soon as it starts moving. Remember, everything has inertia whether it's moving or not. Momentum, by definition, something has to be moving. So when you play pool and you hit the ball, you have given it momentum. That mass is in motion. And when it hits another ball, it transfers a force to that ball, and that one starts moving, so then we say that one has momentum. So momentum is mass in motion. We talked about the law of conservation of mass, this idea that mass doesn't get created, it doesn't get destroyed, it maintains a constancy, we'll say. The law of conservation of momentum is very similar. The total momentum of two or more objects after a collision is the same as it was before the collision. So in other words, this mass in motion is conserved. When you hit a pool ball and it's moving, it has momentum. When it stops moving, it isn't because its momentum just disappeared. It transferred its momentum to this ball right here, which now has mass in motion. Now, eventually, will a ball traveling across a surface slow down? Yes. Does that mean that momentum is being lost? Well, no, it's transferring some energy to the pool table through friction. There are a lot of forces that go on. But we basically just need to understand that momentum is conserved. This ball hits this one, this mass goes into motion, so we don't lose momentum. It just gets shifted around. You can see this if you would have one ball and you'd hit an entire triangle, I don't know what they're called, of these pool balls right here. The ball that hits it would stop, but it just transferred its momentum, let's say, to these, and they started moving. Their mass went into motion. So overall, we say the momentum is conserved. How is this related to Newton's third law? Well, when I have a pool ball and it hits these right here, for example, it hits this front ball, it exerts a force on this ball, but this ball also exerts a force back on the ball that hit it. How do we know? Because the ball that hit it stops moving. And then this ball exerts a force onto this one, which exerts a force onto this one. So there are lots of action-reaction pairs when these are all lined up. So the law of conservation of momentum ties right into Newton's third law. So there is an equation for momentum. Let's look at the symbols. We use little p as momentum. We use little m as mass. We use little v as velocity. So here's our equation. Momentum equals mass times velocity. The unit for momentum is kilograms times meters per second. Ooh, that's a mouthful. The unit for mass is kilogram, and the unit for velocity or speed is meters per second. So we're familiar with these. The one for momentum looks kind of funky. Here are a couple of practice problems for you. Calculate the momentum of a 6-kilogram bowling ball moving at 10 meters per second. So here's my mass. Here's my velocity. I multiply those two together. 6 times 10 gives me 60. And here's that funky unit, kilograms times meters per second. You just stick the unit right onto the end. So that's how you use the equation. Part 2, would it hurt more to get hit by this bowling ball? If a bowling ball was flying at you, a 6-kilogram bowling ball at 10 meters per second, would that hurt more? Or if a 100-kilogram boulder was moving at 0.5 meters per second towards you? Okay, 100 kilograms probably wouldn't be a boulder, but a large rock moving at 0.5 meters per second. Which one would hit more? Let's do the math. If we calculate the momentum, a 100-kilogram object moving slower would only have a momentum of 100 times 0.5 gives us 50. So we would say the bowling ball actually has more momentum. Even though it's smaller, it's moving faster. So it would probably hurt more to get hit by the bowling ball. All right, those are your notes about Newton's third law.